Hello. So, in this video, I'm going to give you another example. Now, the research question we would like to answer is, does paying high tuition pay off? So, so we are studying the relationship between tuition and salary. So I'll define the basic events this way. T stands for high tuition. So you graduate from a high tuition school, and say S stands for high salary. So high tuition and high salary. So simply consider tuition is high and low, or and salary is high or low. So it's also 2 by 2 structure, and the structure is similar with what we have studied in the previous videos. So first, what probabilities do you need to calculate and compare to answer this question? Try to answer it by yourself. Okay, so if you make your mind, what we are going to do is we are going to compare two groups. That's what we have done. And the two groups are defined by the tuition level. So one group paid high tuition and the other group paid, say, low tuition. And for each group, we'd like to see how many of them receive high salary. So high salary, probability of high salary may be different across these two tuition groups. So that's what we are going to compare, how we are going to make comparison. So in here, this is the answer. The condition is, the first group is tuition. The condition is high tuition, and the other group is low tuition, tuition complement. So T complement is low tuition group. And across those two groups, we calculate and compare probability of high salary, right? Probability of high salary if you went to high tuition school compared with the probability of high salary if you did not go to a high tuition school. That's what we are going to compare, right? Okay, so once we set up the problem and what we need to know, now look at the data. And I made up numbers again. It's a fake data, fake numbers. And we have the usual 2 by 2 probability distribution table. 2 by 2 table is given this way. And based on this table, we would like to calculate these conditional probabilities. Do it by yourself. I'm not going to give you any more hint. So calculate those two probabilities and determine what's your result of the comparison. It may take time, so stop the video. And if you have calculated those two conditional probabilities, you must have realized that they are the same. The answer is B. B is the answer because first, probability of S given T is based on the first row because only the first row satisfies the condition T. Out of the first row, 11.25% earns high salary. So the ratio is 25%. Similarly, the second row, the second row, this condition implies the second row. The second row among the second, from the second row, 13.75% receives a high salary. So that ratio is also 25%. So based on the data, of course, unreal, it's not real. Based on these numbers, we can say that the tuition does not affect the chance of high salary, right? Either you attend a high tuition school or low tuition school, the probability of high salary is the same. So that's our conclusion. This is what we have done in our previous slides and videos. We are going to go one step further. This is a very special case, right? They are the same thing, and we are going to compare them to another probability, which is just an unconditional probability. So if you calculate unconditional probability of high salary, the probability of high salary unconditionally, so we are using 4 numbers together, and this event S, includes two outcomes, so its probability is again 25%, right? And it's like, which is the same as these conditional probabilities. So we found that unconditional probability is also equal the conditional probabilities, which makes sense because the probability of high salary is not affected by tuition. That is, regardless of your tuition level, the probability of high salary is 25%. Even if you graduate from a high tuition school, it's still 25%. Even if not, still 25%. So no matter what you condition based on the tuition, right, the probability of high salary does not change. Always 25%. This is a special case, a very interesting and special case. We are going to define such a case as statistical independence. So we say that two events, A and B, are statistically independent or simply independent if those probabilities are the same. So probability of A unconditional probability equals to the probability if B happened, or probability if B did not happen. So no matter what happened to B, probability of A is the same. And also, this is a special case, so you may switch the role of condition and event. So also, probability of B is not affected whether A happened or not. So that's an interesting example, and it's actually very important in statistics in general, because later we are going to assume a lot of data satisfy independence assumption. Like independence will be used as assumption. So interpretation. You may interpret it many in different ways. Like B is not effective to change A, so we develop a medicine to cure a disease A, but the probability of like recovering is the same, so ineffective. Or information about B does not help predict A, right? The probability of A happening does not change whether whether you observe B or not. Like even unconditional probability is the same. Or between different groups of B, the outcome is the same. That's what we how we interpreted the examples in here. Between tuition groups, the high salary probability is the same. So there are you can put many different ways of interpretation on independence, right? And in economics, we use, for example, like this: today's stock returns independent of tomorrow's or not. If yes, if this question is yes, that means today's stock market information does not have any prediction power for tomorrow's. So it's an interesting question. Now another example: Chinese GDP growth rate, is it independent of the United States GDP growth rate or not? If yes, then like predicting Chinese GDP growth does not help in prediction of the US. GDP growth, right? Or if GDP, China and the US are independent economically, then you can diversify your assets like across China and US, right? So independence itself is one of the key concepts in many research questions and in many analysis. So we are going to study it a little more carefully. What we also additionally, another nice property of the statistical independence is this simplification of the multiplication rule. So earlier I gave you general multiplication rule is given this way. Probability of intersection is multiplication of conditional probability and unconditional probability. But conditional probability is like not easy to calculate. But what we have here is if you know that A and B are statistically independent, that means conditional probability equals unconditional probability. In the end, the probability of intersection becomes a very simple multiplication of two simple probabilities. So this is a special multiplication rule. And remember, in chapter 1, we learned general addition rule and special addition rule. At that time, the special addition rule was for probability of union. That's the difference. But the special addition rule was particularly about the probability of union when two events are mutually exclusive. Remember, go back to chapter 1 and see the condition for special addition rule. At that time, we need to assume mutual exclusiveness. But here, the same role is played by statistical independence. You need statistical independence condition to have a special, simple multiplication rule like special addition rule. So these two rules have like parallel structure. However, I can certainly say that independence is much more important than mutual exclusiveness, and those two are totally unrelated. So even if two events are statistically independent, it does not imply they are mutually exclusive or not. Vice versa. So just they are parallel, but there is no relationship, mathematical relationship. That's another thing we can learn. So now then, as I said, independence is one of the most important concepts in statistics. And then in many cases, we want to verify whether two events are independent or not. Like checking independence itself can be an important task in many analysis. To do that, just if you want to answer if A and B are independent or not, there are two different ways. Because independence implies these two results. Like one is that the unconditional probability and conditional probabilities are the same, no matter what happened to B. That's one result we can use to check independence. And the other is the special multiplication rule. If A and B are statistically independent, this must be true. So if one of them is true, then we can say A and B are statistically independent. If they are not, then both fail. So you can see, like by checking one of them, you can simply see whether independence is true or not, holds or not. So again, put it this way. So when you need to answer whether they are independent or not, choose one of them, one of the two equations, and prove or disprove. If one of the equation holds, then they are independent. If not, then not, right? That's what we are going to do. And we are going to use these equations to check the independence from the imaginary data in the next video. See you later.